So the next example of stationary waves will be in air columns. So we can either use closed tubes or open tubes. So what are closed tubes first? Let's talk about closed tube. So closed tube or closed pipe, they call it, is when this side is closed. But of course you cannot close both sides. So open pipe or open tube is this side open, this side also open. But closed tube means this side is closed. So how do we generate stationary waves? Remember, we need to have two waves traveling in the opposite directions, which are identical right now. So you're going to use sound waves now. So you have a speaker connected to a signal generator. That means you can adjust the frequency of the sound coming out from here. So the sound waves which come up from the speaker will travel along the tube, will hit this end here and bounce back. So then you will have two waves traveling in the opposite directions, and then you get stationary waves. But you remember, this is using sound waves. So how do we know where resonance is occurred? That means how do we know when stationary waves are formed when we cannot see, right? So number one, we can hear the sound. That means when you increase the frequency from low to high, so when you increase frequency from low to high, the pitch will change from low to high, but the amplitude is still the same one. So it'll be something like from a low, then it goes to goes to higher frequency, like that, but same amplitude. But once you reach resonance, you'll be exceptionally loud. So something very loud already. So that's when you'll get stationary wave. And if you want to see the pattern, right, you can sprinkle lycopodium powder or dust, which is very fine, as long as it's very fine and easy to move. When you see when the stationary waves occur, you will see the powders will form. They call it heaps at certain position. So these heaps of dust or heaps of powder will be where the notes are. So why would the notes here form the heaps of dust or heaps of powder? It's because your stationary wave using sound waves is a bit different now. Now sound waves are transverse or longitudinal waves. So if they're longitudinal waves, that means the sound waves move like that, which is the air molecules vibrating this way. So when you send in the wave, it will travel this way and then bounce back, right? So remember at the nodes, right, there is no vibration of molecules. So that means here, all there's no vibration of air molecules. But on either side of the node, remember the molecules are moving in anti-phase. If you're talking about transverse wave, that means if there's a node here, transverse wave means they'll move anti-phase like that, one up, one down, right? But in a longitudinal wave, where this is a node, they will move this way. This is called anti-phase. They move opposite directions. Do you understand? So therefore, if this is a node where there's no air movement, but on either side they're moving this way, like this, so wouldn't it push the dust and accumulate in the middle? So that's why you have the dust where the nodes are. Okay, so now let's see how to predict the frequencies and the wavelengths again. Now, for a closed tube, there's some rules to follow. So if I were to draw a closed tube like this, no matter what happens, this side must be an empty node, because this is where the sound comes up from the speaker. So it's free to move on. But on the other side, because the air molecules cannot move because it hits the wall, it will be a node. So no matter what happens, this has to be an antinode, this has to be a node. And the general shape of a stationary wave is, remember I showed you with something like this. This is the general shape of a stationary wave. So you must always start with an antinode and you must end with a node. So if you travel along here, the first time you start with an antinode and you end with a node will be to here, correct? So which is why the first shape you will get is this. Start with an antinode and you must end with a node. So how many wavelengths is between an antinode and a node?
1/4.
It's a quarter of a wavelength. So here the formula will be lambda over 4 is equals to L. So therefore lambda equals to 4L. And this is the lowest frequency that resonance will occur, so we will call this as F1, for example. Okay, now the next time you get resonance is, remember you must start with antinode and end with a node, right now. The second time you end with a node will be here. So you get the shape from here to here, which is this. So how many wavelengths is this? half plus a quarter, so it's 3 lambda over 4. So 3 lambda over 4 equals to the length of the tube L, which doesn't change. So therefore your lambda, make it as a subject, you get lambda equals to 4L over 3. Okay now. So now from here to here, can you see the wavelength has divided by 3 from 4L to 4L over 3? So the frequency you must times 3. Okay, because the frequency is inversely proportional to wavelength. So a third time you get resonance will be starting from here and end at here. Because you must end with a note, which is why this is your third time. And the third time you get resonance, how many wavelengths is this? This is 1 wavelength, this is a quarter. So it will be 5 lambda over 4 equals to L. So therefore your lambda will be equals to 4L over 5. So you refer to the start, initially was 4L, now it's 4L over 5, that means you divided by 5. So therefore the frequency must times 5. So that's how you count. So there's a general formula. Now you notice that your lambda, you will see you get 4L over 1, 4L over 3, 4L over 5. So it's lambda equals to 4L over n, but your n must only be an odd number. You will not be like just now, the stretch string was 2L over n, n can be any integer. No. This 4L over n and n must only be odd numbers. That means the first time you get resonance is when n equals to 1. Second time is when n equals to 3, not n equals to 2. And third time is when n equals to 5. Okay, so that is for a closed tube. Now for an open tube, it's a little bit different. Okay, so what will happen is, no matter what happens, when you want to see the shape of the stationary wave, this side must be an antinote, this other side must also be an antinote. So how are stationary waves formed? Because people don't understand how is it reflected since this is empty. So imagine the sound waves coming from here, the speaker is here. So it travels, vibrates. So means only the air inside the tube will vibrate, right? But once it reaches the end here, there's like an invisible wall of air outside that it has to push all together. So that causes it to bounce back because the mass of the air outside is bigger. But because air can move, so it can push and come back. That's why this is also an antinote. Okay, so the general shape of the stationary wave, as usual. Okay, let's draw it out. So this is a general shape for a stationary wave. So we must start with an antinote and we must end with an antinote. So the first time you will get this shape is here, because this is when we start with antinote and end with antinote. So you'll notice that this is the first time you get resonance. So the length of the tube is L. So how many wavelengths? Half. So lambda over 2 equals to L. So therefore, lambda equals to 2L. So we call this frequency the lowest frequency F1. Okay? So second time we get resonance, remember you must start with antinote and you must end with a note. So second time is here. So you can draw here. That means from here to here. So this is your second shape. So therefore, how many wavelengths is here? So antinote to antinote half, antinote and another half. So total, 1 wavelength. So your lambda equals to L. That's it. Right now. So you look at this, originally it's 2L over 1, now it's 2L over 2, right now. So you divided by 2 the wavelength, so the frequency must times 2. And the third time you get resonance, you must start with an antinote and you must end with another antinote here. So therefore, your shape will be from here right up to here, which is this. So how many wavelengths you will get? Half plus half plus half. So 3 lambda over 2 is equals to L. So lambda is 2L over 3. So from here to here, from 2L become 2L over 3 means you divided by 3 the wavelength, so frequency must times 3. So that's how you get your resonance. Alright, so you notice there's a general formula as well. So you notice that it's 2L over 1 to L over 2 to L over 3. So lambda equals to 2L over n, where your n is an integer. So doesn't it look familiar? It actually is the same formula as your stretch string. So why does it have the same formula as a stretch string? It's because in a stretch string, you start with note, end with note. Now you start with antinote, you end with antinote. So they are similar. The only thing that's different is your closed tube, because one side is antinote, the other side is a note. So it's not the same on both sides. Therefore, the formula is for L over N, and it must be an odd number. If they're the same, node, antinode, then it's 2L over N, and N must be just an integer.